Hello everyone, as you can see I have just done a little test to see that this works. So welcome to lesson 1 of physics feedback. So what I would like to do is just quickly go through some of the key points that people generally got wrong, and then I'm going to apply that to some of the questions from the exam that you have just done. And then there'll be some follow-up work for you to have a go at on your own. Okay, so the first thing that was problematic is what weight is. Okay, so weight is a force. Okay, so therefore it is measured in newtons. Now, when we draw weight on a diagram, so if I have a block like this on a table, we always draw it going downwards. Okay, now what I saw a lot of in the test was people drawing weight going in that direction. Weight is always going to go down like that, and we can label that weight, and sometimes we might see it's labeled as mg like that. Okay, now the reason for that is that to work weight out we have to times together mass, which is generally in kilograms, by the gravitational pull of the Earth, or whatever planet we're on, and on the Earth we tend to use 10. Okay, so always we're going to draw weight downwards. Okay, the next thing that was mixed up quite often is this force here, friction. Okay, now friction is a contact force. What that means is it has to be touching to have an effect. Okay, so when two surfaces are touching and moving past one another, if we could see them on a microscopic level, what we would see is these little surfaces, getting caught together like this. Okay, now the grippier or more up and downy these lines are, the more friction. So therefore the kind of converse is also true. If you have two surfaces that are relatively smooth, now nothing's going to be flat, but smooth like that, we're going to get less kind of gripping between them, and so therefore we're going to get less friction. Okay, and finally the other very mixed up force is this one, air resistance. Now air resistance always acts against movement. Okay, always, it's never ever going to go in the same direction as movement. So if I have a car, now a very badly drawn car, there's my car, and it's travelling in this direction, this is the engine force, then this is going to be the air, I've gone off the page, air resistance. It's always going to go in the opposite direction. My car is travelling in that direction. Okay, if though I have a little person who's jumped out of a plane, so let's say here's my person who's jumped out of a plane, there's my little stick person. If they are falling, which is in this direction, then the air resistance is going to go in that direction. So this then would be their weight, because weight always goes downwards, and then their air resistance is going to go in that direction. Air resistance is not the same as wind. Okay, the wind can blow a sail and then it will move in the direction of the sail. Okay, like this diagram here. Air resistance would still be acting against something that is being pushed by the wind. Okay, lastly, I'm going to have to go back up here. The last thing that we haven't really got a grip on is this thing here. So pressure. Pressure is worked out by doing the force that's applied divided by the area of which that force acts on. Okay, so we talked, if you remember, about the bottoms of shoes. If I looked at the bottom of a trainer like this, and the bottom of a high heel, which would have the heel and then just the front bit, wouldn't it? So this is like the bottom of them. This is my trainer, and this is my high heel. I was the same person wearing both of these shoes, so therefore the force would be the same, which would be their weight pushing down on the shoe. Then this one here has a larger area. This one here, if we added up the area of that and the area of that, this is a smaller area. Okay, so the pressure on the floor from this shoe is going to be lower than the pressure on the floor from this shoe. Okay, so this one is going to have a higher pressure, and the reason for that is because we're doing the same force divided by a smaller area, giving us a bigger pressure, or we're doing the same force, their weight, divided by a larger area, which is the trainer, which is going to make this number smaller. The pressure is smaller. Now I'm not going to go into all the maths and examples of why that is. It is the concept that is important. So when we're talking about the arrows and pushing into, there's a question later on I'll have a look at about the front of an arrow. Now if you imagine a blunt arrow, so this is the front of the arrow, compared to a very sharp arrow, again the same applies here. So we've got the same force because they're coming from the same bow pulled back by the same amount, but this one has a larger area and this one has a smaller area. Therefore, if we apply the same as we did here, this therefore becomes a smaller pressure and this becomes a larger pressure. What that means is it is more likely to stick into the dartboard or whatever those things are called that you fire arrows at. What are they called, Joe? Target things. Bullseye things. So we'll talk about the question with the arrow in a short while, but that's the kind of concept. So lots and lots of us were saying the arrow has a pointed end, which is absolutely right, therefore it's more streamlined, which is also absolutely right, so therefore it sticks to the target. That is true, it will be more streamlined and it will have less air resistance, but the question is really about the size of the tip here and the fact that this one has a larger pressure. Okay, so things to remember then. Weight always acts downwards. Okay, it is a force and it's in newtons. Friction is a contact force. It only happens if two surfaces are touching, and the more grippy the surface is on a microscopic level, the more friction. So therefore the converse, the smoother the surface, the less friction. And that was really, really heavily confused in the test. I had a lot of people talking about friction being a good thing in the case of the person going down the slide, and therefore the more friction the faster he'd go, which is the completely backwards. Finally, air resistance always acts against movement. It doesn't matter which way you are moving. And this one moving in this direction, the air resistance goes that way. In this one, the air resistance goes up because they are moving downwards. Okay, so that can change around which way you draw the arrow. However, it doesn't what am I saying? Forgotten, because Joe switched the tap on, which has put me off. Okay, let's move on. Let's talk about the test itself. Right, so I'm not going to go through every single question right now. There's just a few key things that I would like to mention, so I'm not going to mention this one at all as yet. So this one is the first one, which I just wanted to have a quick look at. So it says, draw an arrow on the diagram to show the direction of Alan's weight while he is upside down. Now, it doesn't matter that he's upside down, his weight always acts downwards, okay, as we said. So I'm going to write that on there. That's his weight. It always goes downwards, even if he is upside down. Okay, I'm going to come back to mass and weight later on in the week, so we'll come back to this one. This was the one that I was a little bit worried about with weight as well. We have the rope is pulling Amy. Draw an arrow on the rope to show the direction of this force. So we got a lot of correct answers here. Okay, it's being pulled. She's being pulled in that direction. Now, I had an awful lot draw an arrow to show the direction of Amy's weight, label the arrow B. I had loads and loads of you drawing that. Okay, that is in fact air resistance. Oops, resistance. That is not weight. Weight, as we've said, or I've just said, always goes down. So that is not right. That is correct. Okay, weight is going to go downwards always. Okay, finally, a couple of things here. So it's this one here. So Anil is going down the helter-skelter slide. What's happened? Anil goes back for a second go. This time he sits on a smooth cushion instead of a mat. So the mat then is more grippy, and the smooth cushion, as it kind of implies here, is smooth. So therefore this one is going to have less friction, and this one is going to have more friction. Okay, so we have to say he goes much faster on the cushion, give a reason for this. Okay, so smooth cushion, less friction, that is the reason. I had loads of people saying that there was more friction and that was a good thing. So in this case it is less friction because of the smoothness of the cushion, okay, as opposed to the grippy mat. So less friction, therefore less gripping together of the two surfaces means that Anil can go down the side more quickly. The other thing that I just wanted to mention is the arrow question. We've got the drawing shows a boy with a bow and arrow. He's holding the arrow, pulling it back. So here he is pulling the arrow back. Two horizontal forces act on the arrow. These are the force exerted by the boy's hand. Oh, sorry, and the force exerted by the string. The arrow is not moving. Okay, so at the moment it's not moving. He is pulling it back with 150 newtons. It says here, so we've got 150 going that way. Now, if it is not moving, that means that we've got balanced forces, so therefore we must have 150 newtons going in that direction. Okay, so what is the size of the force? It must be 150 because it is balanced. Okay, it's not moving, and we know that stationary means balanced. Okay, now consequently when the boy lets go of the arrow, it starts to move forward. So what you're doing is you're unbalancing the situation. Okay, you're taking this one away, leaving just that one. Okay, if we've got an unbalanced situation, then what we're going to have is only the forward force. Only the forward force, and that means we've got 150 versus nothing, so we've got an unbalanced force. That also means it's going to get faster. If you remember, unbalanced means getting faster or getting slower, a change in speed. Okay, that is the reason that the arrow moves forwards. Okay, finally, oh no, not finally, we're nearly there. The arrow flies across a field to his target, not a whatever I said earlier. Two forces acting on the arrow while it is in the air. Air resistance acts in the opposite direction to movement, as we know, we've just said that. Gravity acts downwards. These two forces cannot balance each other, even when they are the same size. Why is this? Now, loads of you did get this, but quite a few of you got confused with this. So if we imagine this situation, let's say it's 150 for argument's sake, going in that direction. No, it's not that because it's air resistance, so sorry, it goes against the arrow, so it's 150 newtons. And the gravity, we don't know what it is, but let's just say it's 20 newtons. Okay, now those are different, so they wouldn't be balanced. But even if this was 150 newtons, they're still not balanced. The reason is one is acting horizontally and the other is acting vertically. Okay, you need to remember that forces only balance and unbalance if we're talking about the ones in the same plane. So these, when they were both there, they're balanced because they're both in the horizontal. If we look back over here at these ones, These are balanced because they're both in the horizontal. These are balanced because they're both in the vertical. However, if we have a situation where we've got one going that way and one going that way, then they're not balanced. They can't balance because they're not in the same plane, okay? So this could, oops, that was supposed to be an arrow. But if we have this situation, then we cannot talk about balanced and unbalanced because they are acting on opposite planes from one another. Okay, and I don't mean aeroplanes, I mean the horizontal or the vertical plane. Okay, the arrow has a sharp pointed end. Now this is where we went, we just had lots of good guesses, but I don't think we fully understand what pressure really meant. When the arrow hits the target, the sharp point exerts a very large pressure on the target. Why does the sharp point exert a large pressure on the blunt, larger pressure than the blunt end? So this is to do with the fact that the sharp point has a smaller area, okay, and therefore a higher pressure. And remember, that is because we've got pressure is equal to force over area. So this remains the same and this gets smaller, then this must get bigger. And we're going to do a whole lot on that later in the week. Okay, so that is it for now. I'm going to attach to this video, that's 17 minutes of video, so I'm going to attach to about 45 minutes worth of work to have a go at alongside this. Okay, thank you very much. Bye.